Hi, and welcome to 5.5 Inclined Plane, Part 2. All right, let's go to the next one. Number 2 says, a 1,000 kilogram car is parked on a dry asphalt hill that is inclined 35 degrees above the horizontal. Does the car remain at rest or slide down the hill? Now, you got to think about this. Have you ever parked a car on a hill or been in a car parked on a hill? 35 degrees is pretty steep, but it's not unheard of. I would hope that on this dry asphalt, the car remains at rest. So that's going into it, we should probably assume it's going to want to stay at rest. But let's see when we do our calculations. So again, you draw your free body diagram. Very important for these types of problems. And we have the weight going straight down to the center of the planet. And we have the normal force acting perpendicular to the hill. And we have the frictional force acting up the hill. Remember from the previous video, the type of friction we're looking for is the static friction. It starts at rest, and we want to know what is the maximum static friction that exists between these two surfaces before it starts slipping. If the weight is greater than the maximum static friction, it's going to slide. And when I say weight, I mean the component of the weight that acts parallel to the hill. Because as you remember from the previous video, we switched, instead of this being our x-axis, we made the surface, the inclined plane, is the x-axis. And this is our y-axis. And we said it was more convenient to do so because that means the normal force and the frictional force are both agreeing with those axes, and we only have to do some work in breaking up Fg into two different components, instead of the normal force and the frictional force. So even though it seems weird, trust me, we're making our lives a little easier. So you draw the component of the weight that acts perpendicular to the hill, and you draw it just long enough so that when you draw in the line, see how that's parallel? This is FG parallel. You don't draw it longer than that, all right? Because you want this to be a right angle. Because these two are just parts of a whole. They're parts of that weight. And we know, if we know what this angle is, we know what this angle is. In this case, it's 35 degrees, and this is 35 degrees. So that's the situation. That's what we're looking for. If we figure out what the static friction is, the maximum static friction is, and we look at this, FG parallel, if FG parallel is greater than the maximum static friction, it's going to slide. If it's less than the maximum static friction, which we predicted will be, it's going to remain at rest, hopefully. Hopefully we don't have cars just sliding down all these hills as they're parked. Okay, so let's write in some givens. The mass is 1,000 kilograms. We can assume we're on Earth. Theta is 35. You could draw it in right there. And it's on dry asphalt. And cars, we could say, have rubber tires. So we're going to look for mu s, dry asphalt and rubber. Let's see. Dry asphalt and rubber. So that was from the wax ski on snow problem. Dry asphalt is right here. Are we looking for static or kinetic, people? We want to know what the static coefficient is, 0.85, because it starts at rest. So 0.85. It's pretty high for coefficient of friction. And I think that's all the info that we could plug in for now. So we're looking for FFS max. All right. In order to do that, we need to know what the normal force is. And in order to know what the normal force is, we need to know what FG perpendicular is. And to figure that out, first we need to find FG. So let's find FG. Here's our free body diagram. These are our givens. Fg is equal to mg. Fg is equal to 1,000 times negative 9.8. So Fg is equal to negative 9,800 newtons. That's a lot, but remember we're talking about a car, so that's okay. Then we're going to break this into components. All right, FG perpendicular is what we're looking for. Is this opposite, adjacent, or hypotenuse? See our right triangle? FG perpendicular. Is that opposite, adjacent, or hypotenuse? That's adjacent to the angle. And FG, is that opposite, adjacent, or hypotenuse? That's the hypotenuse. So we have adjacent and hypotenuse. Are we going to use sine, cosine, or tangent? That's right, we're going to use cosine. And in the previous question, in the previous video, we saw that we could use our shortcut just like that. If you want, you could go back to the previous video or just do cosine is equal to FG perpendicular over FG, adjacent over hypotenuse. But this is kind of the shortcut that makes these just that much a little bit easier. And we'll take what we could get because there's a lot of steps in these types of problems. So FG perpendicular is equal to 8,028 newtons. All right, 8,028 newtons. And now we know what the normal force is because the forces are balanced in the perpendicular direction, meaning we're not accelerating through the hill and this car isn't being launched off the hill. The forces are balanced in that direction. So the normal force is also equal to 8,028 newtons. Now we're ready to do the frictional force formula. Fs max is equal to mu SFN. What is the maximum static friction that can exist between these two surfaces? 0.85 times the normal force, 8,028. FFS max is equal to 6,824 newtons. So this is 6,824 newtons. That's good to know. So the maximum force that can exist, frictional force that can exist, is that. So what is the force exactly that's causing us to go down the hill? FG parallel. Let's figure out what that is. FG parallel is equal to FG, do you guys remember? Sine theta. How do we know that? Here's your angle. This is opposite your angle. We're also going to use the hypotenuse. Yes, you could use the Pythagorean theorem, but this is the physics way to do it. All right, so FG parallel is equal to 9,800 sine 35. It's the same every time, so it's good to get you into the habit of doing it. And you get 5,621 newtons pulling you down the hill. Is that enough to overcome the frictional force? It is not. It is not enough. So you have this. We have this. This force is less than the maximum static friction. So the static friction is enough to keep it at rest on the hill. The forces will be balanced. So the actual static friction is equal to 5,621. Remember, the static friction increases with the applied force. So it didn't reach that 6,824 newtons yet. Right now, the forces are completely balanced. All right, we just know what the maximum is. Okay, so if we wanted to be like more precise, now that we know what's going on here, technically we could write FFS is equal to 5,621 newtons, showing that everything is balanced. This is equal to that, this is equal to that, and the car remains at rest. Again, because the parallel component of the weight is less than the maximum static friction. So if it does slide down the hill, who cares? We're not doing these. We did questions like this in the previous video. NA. What's NA stand for? Not applicable. I can't apply that to that. It doesn't happen. All right, see, if it doesn't slide down the hill, which it doesn't, what is the minimum angle that would make them slide down the hill? Interesting. So let's increase theta, right? It needs to be a steeper hill. As we increase theta, the normal force decreases, and also the parallel component of the weight increases. So it's getting steeper. And at some point, it's going to slide down the hill. So let's see. Let's redraw our diagram here. This is now theta. We don't know what it's going to be. But we know FG. We know this is still FFS max. Let's use this maximum value, because as soon as we reach that maximum value, it's going to start slipping. And this is the normal force. Actually, we're not going to, what we need is these two here. This guy and this guy are always going to be balanced because the normal force changes with the perpendicular component of the weight. So in that direction, they'll always be balanced. But in this direction, we want to know when FG parallel is going to be equal to the maximum static friction. Because if you increase the angle just a slightly bit more, then the parallel component will be slightly bigger, enough to overcome the maximum static friction. So again, we want to know when this component is equal to this frictional force. So let's make an equation. Okay, so we want to know when the maximum static friction is equal to the parallel component of the weight. So FFS max, when that is equal to the parallel component of the weight, you increase the angle slightly more, and then it's going to start moving. So what exactly is the maximum static friction equal to? We know from our formula, FFS is equal to mu S Fn, don't we? So let's plug that in over here. Mu S Fn is equal to Fg parallel. Well, what's the normal force equal to? The normal force is equal to the perpendicular component of the weight. So let's rewrite that as Fg perpendicular is equal to Fg parallel, like the coefficient mu s times Fg perpendicular. Now, looking back, when we were finding the components, we had these handy equations, these little shortcuts. Let's plug those guys in for perpendicular and the parallel component, because this angle, even though we don't know what it is yet, is still theta. So mu s is times Fg cosine theta. That's from the shortcut. It's the adjacent and the hypotenuse. So the shortcut makes it Fg cosine theta is equal to, now the parallel component, that's opposite, and we'll use the hypotenuse. So again, the shortcut tells us it's equal to Fg sine theta. So if we want to get these thetas all to the same side, let's do this. Divide by this term. Now Fg divided by Fg, those two cancel out. And you're left with the coefficient of friction on one side, mu s, is equal to sine theta divided by cosine theta. Now in my class, this is the only time you're going to have to use a trig identity. Do you guys remember what sine divided by cosine is? From your math classes, you could look it up online. What's sine divided by cosine? The coefficient of static friction is equal to tan theta. That's the, sine to cosine, sine divided by cosine, that turns into tan. That's a trig identity. Now, we're ready to plug in numbers, but there's only one number we need to plug in, the coefficient of static friction. Actually, we could even solve further before we do that technically. We're looking for theta, right? So we got to do the inverse tangent to both sides. So theta is equal to the inverse tangent of the coefficient of friction. We're just plugging in one number. The coefficient of friction is 0.85. So theta is equal to 40.4 degrees, which we weren't at. That's a pretty steep angle. We weren't quite there in the problem. We were at 35 degrees. If it was at 40.4 degrees or a little bit higher than that, then the parallel component of the weight would all of a sudden become greater than the maximum static friction. All right, that was fun. Have a good day.